All right, hi everyone. So let's continue the open interval methods for the root finding algorithms. So an alternative or an alternative to the Newton-Raphson method is the secant method, oh, wherein this method solves the major weakness of the Newton-Raphson method, no? The weakness of me, myself, and you guys, my students, which is the differentiation, no? So the evaluation of this derivative is difficult, and usually it will be much more computationally complex to create rather than just addition, subtraction, and so on. So to circumvent this problem, instead of a derivative, we can approximate the derivative by utilizing the numerical derivative. You know? So this f prime of x can be approximated as a change in y. No? So we know that the derivative basically is the infinitesimal change in y versus the infinitesimal change in x. But we could approximate this as the change in y over the change in x at discrete values. And also this change in y, basically the difference in f and the difference in x in the denominator. Okay, so we have already discussed this, and this is called the numerical derivative, just in an alternative format, no? So using this derivative, substituting this back as an approximate derivative, we now have this formula. So this formula or this iteration function is similar to the regular falsi, ano? And we will discuss later the comparative difference or the comparative efficiencies of the regular fallacy and the secant method. They are actually similar. So graphically, how do we represent this iteration scheme or this root finding algorithm? So Newton-Raphson finds the tangent line, but the secant method finds the secant line. So this tangent line can be approximated through numerical derivative. So instead of a tangent, we have this secant line that intersects our curve into 2 points. So this secant line, we will find a new approximate here, and then go here, and then go here, and so on. So this iteration will arrive at a solution, no? At most cases. So one thing to take note here is this iteration function, and similar to the regular falsi or bracketing methods in general, since we are trying to find the numerical derivative, we want to have two initial guesses for our starting condition. Ano? So we want to use previous, we have two previous approximate values to determine our present values. So our n here, no, just be mindful of this. Our n here represents, n plus 1 first, no? So n plus 1 represents the present value or the new approximation and represents the previous as well as the n minus 1. Okay, previous. Okay, so we have two previous approximation, and this is the most recent one before this. Okay, so let's try solving the root of this equation using the secant method with initial guesses of 2 and 1. Ano? So we have two initial guesses for secant method, and then the stopping criterion is 0.01% of the relative or the approximate error. So how do we do this? So remember first, the iteration function is x sub n plus 1 is equal to x sub n minus, we have x sub n minus 1 minus x sub n, and then we have f of x sub n over, we have f of x n minus 1 and minus f of x sub n. So this is the iteration function that we will use, and we want to substitute the value of our functions in this formula. So the function here is this, but we want to substitute this x sub n and x sub n minus 1. So again, now to take note of this, so that we can remember, n plus 1 is the present value, and then n is the previous, or to be specific, the most recent previous. And then the other previous one is n minus 1. And then our iteration scheme will be simplified, no? So let's substitute the values here. X sub n. And then, to change things up a bit, I will make this n into letter B for our calculator technique, and then A for the previous one. Now, for x sub n, we have x sub n minus, so x sub n minus 1. Sorry, I have to change this one as well. Ano? So x sub n will now be, so ito yung x sub n, this will be x n minus 1. Okay, so for x sub n, we have B minus, we have A minus B, okay? And then f of x sub n, so this is the function. So x sub n is B, so we have to substitute B to the 6th power minus B minus 1 all over, so f of x n minus 1, so this should be A. So substitute the A here, we have A raised to 6 minus A minus 1, and then minus, we have B raised to 6, so for xn, which is letter B, substitute the values here, and then this will be your iteration scheme. For the percentage relative error, approximate error, we have the present minus the previous over the present times 100%. Okay, so D is the present and C is the previous. Okay, so we are ready now. We have set up the equations. We can now do the iteration of this scheme. So for this iteration scheme, we will only have 3 columns. Okay, so the iteration number, the approximate value x, and then the percentage approximate error. So for the zeroth iteration, basically just the initial guesses. Actually, we have 2 initial guesses. So we have 2 zeros here. So you actually can do this 2 and 1 or 1 and 2, depends on you. But to make things consistent so that we will have the same answer every time, okay, again, this will work, no, either 2 or 1 and then 1 and 2. So for this to be similar to all of us, we will make the first iteration or the most previous approximation as the lowest value. So the lowest value is 1 and the next value is 2. So that we are consistent. And also we will do this every time so that we will arrive at the same iteration for every scheme. So we do not have yet our approximate error. So we have to make this blank first, no? This could be a previous, no? Yes, but since we did not did yet the iteration scheme, we will start with this, okay? So for the formulation, we have our calculators. So for the calculator, we will have to input just this one. So using your calculator, we have alpha B minus, we have A minus B, and then alpha B raised to 6 minus B minus 1. And then over, we have alpha A raised to 6 minus alpha A minus 1 minus alpha B raised to 6 minus alpha B minus 1. And then substitute the values. So what is A here? The most, the B here is the most recent value. So 2. Okay, so this is the most recent, guys. And then this is the previous or the other previous one. So we have to input here as B, as A yung 1. Okay, so B here is 2. The last one is 1. So the approximate value here is 1.0161. Now for the relative error, so for the approximate relative error, we have to input again a new function, so d minus c, okay, and then times 100 calc. So what is the present? So the present here is 1.016, and then the previous is 2 or 1. It should be 2, ano, the most recent only, so the approximate value, right, will be C. Okay, so they have 96.83. So we have 96.83% for our first approximate error. And then substitute this again. So our previous or the most recent value right now is 1.0161. And the previous to that is 2. And then we will have 1.036306. So for the second iteration, okay, we will now find the relative error or the approximate error, 1.0306 and 1.0161. So the answer is 1.4069, 1.4069%, and continue. So I'll just continue here. Okay, the most recent previous 1.0306 and then 1.0161. So 1.1757, 1757, and then for the approximate error, so calc again 1.1757, 1.0306. So 12. So it got higher, no? So it's okay, no? 12.34, so don't worry about that. It's okay. Okay, let's continue. So calc 1.1757 and then 1.0306, 1.1237. Sorry, I keep touching my nose. Okay, sige. What's the next one? We want to find the relative approximate error. So calc 1.1237, 1.1757. So 4.62, 6276. Okay, so fourth iteration, and then for the fifth, might take longer, no? Let's see. So calc 1.1237, 1.1757. So 1.1337. Okay, and then the approximate error. Yes. Oh, or sorry, 1.1337 and then 1.1237. Okay, 88%. So we're getting closer. 0.88, 21%. Next iteration, okay, we have 1.1337, 1.1237. So 1.1348. So we're getting closer. So calculate the approximate error again. 1.1348, 1.137. So 0.9, 0.09. So 0.0969%. So we're getting closer to our stopping criterion. And then calc again 1.1348, 1.1337. So we have 1.1347. So I think we're getting closer to this. I think this will be sorry, not this one. So the previous is the present is 1.1347 and the previous is 1.1348. Okay, so this will be 0.0088. So this is less than or equal to 0.01%. Therefore, the stopping criterion is met. Then therefore the final answer for the approximate root, which is x tilde, is equal to 1.1347. All right, so that's all for this example. Let's move on to the comparative efficiencies of the secant method and the regular fallacy. Yeah, sige. Secant method muna. Computationally, secant method is more efficient than the Newton-Raphson method. Okay. So comparing this secant method and the Newton-Raphson method, secant method will be much better or will converge faster, usually. Although the problem with secant method is it still has some cases wherein it might diverge if the initial guesses are not chosen properly. Okay, and we know that the secant method is the variation of the Newton-Raphson, wherein instead of finding the derivative, we have to approximate this derivative via numerical differentiation. And then for Newton-Raphson method, it requires fewer iterations, obtain the standard accuracy, but the latter needs only one function evaluation per iteration compared to two iterations in the Newton-Raphson method. So comparing this, again, the secant method with the false position method, we can see that the iteration function is actually similar. Yeah, no? So we have the upper, we have the lower for false position or regular fallacy. For secant method, we have the n, no? So n meaning it is the present. Actually, n plus 1 is the present. The most recent previous is n. And then the previous of that is n minus 1. So the difference here actually is that in secant method, the 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 last or the most previous approximation is dropped, no? But in regular fallacy, as long as the sign is not changing, it will not drop that, no? So false possession, it drops the previous estimates based on that bracketing, but the secant method always drops the oldest estimate in pala, no? It always drops the oldest estimate comparing this to secant, this regular fallacy versus secant method. So that will be all for the secant method. Thank you guys and see you in class.